Others, you can ask if you have any doubt, or else we can start today's lecture. If you have any doubt related to week 1, week 2, week 3, you can ask, or we can start it today's content. Okay. So this is the session number 4. So in earlier sessions, we had introduced about the course, motivation to the course. Then week 0 was related to Laplace transforms. So we studied the motivation behind Laplace transforms. That is to convert the differential equation to algebraic equations so that they are easier to solve. Then we studied few of the properties of Laplace transforms. Then in week 1, we studied the basics of the process control. That is, what is the motivation behind the course, what are the common control strategies, first principles models. Then in this second week, we studied with the first order systems. Then after week 2, we went on to study about second order systems, and we solved questions related to the second order system in the last class. So today we will be starting with the week 4 contents. So the first one is the block diagram representation. So given a process, so if you want to draw a block diagram to represent it in terms of all the process control terminology, so how can we do that? Once we are done with that, then we will take a look on different kind of controllers, that is proportional controller, integral controller, derivative controller, then combination of those, PI controller, PID controller. Then we will look onto this on-off control. Then we will just see the comparison of this. After that, we can try solving the numericals related to controllers. So the first thing is, first we need to develop a block diagram representation of a system, especially when we have a control system placed on the top of a physical system. That is, basically, let's consider an example of surge tank. Here we are having an inlet. Let's consider an outlet valve. If we want to represent this physical system, to block diagram representation, that is what we will be studying in control perspective. And after that, we will be deriving the closed loop transfer functions of the given block diagram, and then we will look on different kind of feedback controllers. So earlier, just a brief overview about this. Hello. So we will be studying about this we already studied about this common control strategies, that is feedback control, feed forward control, and feedback plus feed forward strategy. So today we will be specifically looking onto this block diagram for feedback control. Okay, so this is a block diagram of a feedback control. Block diagram representation. So over here you can see different elements. So the first one is controller, final control element. Then this is our physical process, and this is our measuring device. So we have a reference set point. So we have a reference set point, that basically the set point or the target value that we want to achieve. So that is compared with the measurements that has been obtained from the plant or the physical process, and then we compare it using this as a comparator. So it is nothing but the subtraction of both the two terms, and on the basis of that we will be getting an error term. So we feed this error to a controller, and corresponding to the error, depending on its magnitude or trend, it will give us a control action. And this control action is then fed to a final control element, which will give us the manipulated input that can be realized by the process. So basically these are pure signals, but this is a manipulated input that is basically obtained from the final control element, and this control input, this manipulated input, will affect the process, and corresponding to that we will be getting the final output. Why? There will be some disturbances also, and corresponding disturbance, there can be a disturbance transfer function GD. So this is how we represent a overall feedback control block diagram. So basically the feedback control or the block diagram representation consists of the following steps. So the first one is the measurement of process output, such as pressure, temperature, flow, level, composition, etc., using a suitable measuring device. Others, can you mute yourself? You are having the noise. And once we have measured this physical quantity, then we need to compare it with the desired set point. So that is the comparison of the process output with the desired set point, and then we calculate the deviation error, that we termed it as error. So this error can be called as y set point minus y measurement. Then feeding the value of deviation error to the controller, which calculates the appropriate control action to be taken. So yes, basically on the basis of this error, what should be my control action, whether I should be increasing my manipulated input by how much unit. So all those parameters, all those variables are being calculated by this controller, and this control action is being fed to a final control element, that is feeding the value of control action to the final control element, that translates the control action into manipulated form of the process input. So basically this final control element is usually a control valve. So let's say if control valve opens at the flow rate 2, the process might increase. So that is basically the change in the manipulated input. And then we studied comparison of this feed forward controllers, feedback controller. We have already studied this. So the feed forward controllers, we need a basically kind of prediction model or process models. But the advantage of feed forward controller is, as soon as a disturbance is felt by the the controller will try to take the corrective actions. So that is, it takes the corrective actions before the process feels the disturbance. Then such a kind of controllers are good for sluggish system, that is basically when there is large dead time or there is a large delay in the process. Then these controllers don't affect the stability of the process. But there are disadvantages to the feed forward controller, that is, it requires the measurement of all disturbance affecting the system, which is not possible in most of the cases. So disturbances are usually unknown, so it is hard to predetermine them. Then we need a process model for this feed forward controller, and that model would be having some parameters that may change with time or that may show drift with time. So such kind of models are sensitive to variation in process parameters, and it will ultimately affect the performance of the feed forward controller. Then this feed forward controllers requires a near perfect model. So that is why in almost majority of the process, in chemical engineering system, we use feedback controllers. Feedback controller, as discussed, does not require disturbance measurement, and they are insensitive to mild errors in modeling and insensitive to mild changes in process parameters. So basically we don't need an accurate model in this feedback controller. That is why this modeling errors can be neglected. However, this feed forward controller was a reactive controller, but this is not a reactive control, that is it won't react to the disturbance when it is felt. It will only take the control action once the disturbance affects the output of the process. So once the output changes, then only it will take the control action. Then it is bad for sluggish system, that is the feedback controller will wait for the disturbance to travel through the entire process and affect the output. Only then it will take the control action. That is why if the system is very sluggish, there will be a large delay in taking the controller action, which might affect the product quality or the process performance. So that is why such kind of systems are bad for sluggish system. Then it may affect the stability of the process. Then we studied this block diagram representation. Let's just take a case of a physical example. So let's just take again the example of a level control. We are having an input, we are having an output. Let's just consider our objective is to control the level in the tank. That is control H. Then this flow input is not in our hand, so let's just consider it as disturbance. So we can't manipulate or we can't change this flow input. So disturbance, we can write it as flow input. Then the output, basically we can just consider this flow output from the tank. Output of the system Y is equal to F output. So now in order to control the level of the tank, we need to measure this level, whatever this level is. So we can use a level indicator, okay, level indicator or level transmitter. So this becomes our measuring device. So there can be different kind of measuring device in order to measure the level. So one kind can be differential pressure transmitter. So what it will do is it will just measure the pressure at this point and pressure at this point, and then just use the equation P1 minus Pt equal to rho gh. On the basis of that, it can calculate the height of the tank. So this is an example of a level indicator or level transmitter. So what this level transmitter will do is, this level transmitter will be connected through a control loop to this control valve. So this is our control valve or the final control element, and over here we will be having the controller block that will decide what sort of action needs to be taken. So we will be having a reference set point provided. So let's say if the reference set point was I want to keep the level of the tank to 10 centimeter, and at present the level of the tank is 12 centimeter. So there will be an error of 2 centimeter. So this error of 2 centimeter will be fed to a controller, and on the basis of the kind of controller, it will just give us the input that you need to open the valve by 20%. Let's say open the valve by 20%, and then the level will again come back from 12 to 10%. So in such a manner, this control action is taken by the opening or closing of the control valve. That is our basically final control element. So this controller will give 20% opening to the control valve. So this is our final control element. So if we take a look on the block diagram, so we can represent it using, this is our set point, comparator, then we can have a transfer function of the controller usually represented by GC, then transfer function of a control valve, that is final control element, represented by GV. Then we will be having the process transfer function, that is GP, then corresponding to that we will be having an output. Now we need to measure the output, that is the level of the tank. For that we need a measuring device. Transfer function of that measuring device we consider it as GM, and this is again fed back to the system. So this will be plus, and since this is coming in from the opposite direction, this is minus. So this is basically Y measurement. Similarly, there will be a disturbance block function GD. So over here we will be calculating error is equal to YSP minus YM, and on the basis of that we will be taking the control action C, and then we will be calculating the manipulator input U, which will be fed to the process. So this is a brief about the block diagram representation of a closed loop system. Okay, so this becomes a closed loop system. Now if I had to draw the block diagram for the open loop system, then it becomes very straightforward. That is, I'm having an input that is being fed to the process GP, and I am getting an output Y. Similarly, I will be having the disturbance over here, that is GD, and let's consider there will be some effect of that. So disturbance will have transfer function of GD, and the process will be having the transfer function of GP. So basically the output will be the combination of both of these kind of, you can say, inputs, that is manipulator input and the disturbance. So this becomes the block diagram for open loop. So we studied this block diagram from open loop and closed loop. Then we can find the another thing notice to find the transfer function of the feedback controller. So how can we do that? Let's just study. So basically, given any block diagram, if you want to find the transfer function, how can we write it? So let's just redraw the closed loop. Closed loop system. Transfer function. So I'm just redrawing everything again. Controller block diagram, final control element block diagram, process block diagram, disturbance block diagram. Just wait a minute. Then we are having an output, measurement variable, and this. Now if I want to write the transfer function between the output and the set point, that is our input to the system, that is basically Y upon YSP, that is basically output upon input. So what I can do is since we want to, the input is this YSP and we want to write the transfer function across this block Y, and this is again fed back to the system. So this is the entire loop that we want to cover. So in a forward pass, we can see that there are these three blocks, GC, GB, GP. So on the numerator, we will be having the multiplication of all the three blocks. So if the blocks are in series, we can simply multiply their transfer functions. It is GC, GB into GP. Then on the denominator, we will be considering this entire loop. That is, it will ultimately become 1 plus GC, GB, GP and GM. So you can try solving this in the lengthy way. So what you can do is, if this is Y, so this will also be Y, this will also be Y. Then let's consider this was some variable X, so this will become GC times X, then this will become GV into GC times X. Similarly, then you can find the set of equation and then you will ultimately reach these final equations. So you don't need to do the lengthy process in order to find the in order to find the transfer function for the closed loop system. You can just use this analogy. That is, on the numerator will be all the multiplication of all the transfer function blocks in the forward pass, whereas in the denominator it will be 1 plus multiplication of all the transfer functions in the entire loop. So similarly, if we had to write the transfer function for this disturbance, so Y upon disturbance will become, see, if GD is affecting the process, then we can simply write GD GP upon this and all the 5 terms. However, if this GD was over here, then it would have become numerator would only have GD, and on the denominator we will be having the multiplication of all the 5 blocks. So this is how we can find the transfer function given the block diagram representation. Ultimately, later in the class we will be solving the numericals based on this block diagram representation, and that will make your understanding more clear. So now we studied the block diagram representations. So in that we studied about one controller. So we will be now studying what all kinds of controllers are present. So we are studying different kind of feedback controllers. So there are 4 kind of control modes. So the first one is proportional control, second one is integral control, third is derivative control, and the fourth one that we are going to study is basically the combination of all the 3. So basically we can have P controller, then we can have PI controller based on the combination of these two, and then we can have the combination of all the 3, that is PID controller. We can't simply use this integral control action and derivative control action alone, because we won't be able to reach the set point if we use both of these systems, and the systems might become unstable. I think we already studied this in block diagram representation. So the first controller that we are going to study is the proportional control. So this can be kind of called as a proportional control action, and any controller that uses this philosophy is known as proportional controller. So we already studied that in the block diagram representation, that the objective is to reduce the error signal to 0. That is, the error signal is set point, that is YSP. That is, in case of level search tank, I can say that the level of the tank should be 12 centimeter, and then the measured value, that is what is the actual level of the tank in the system at the current instant. So let's call just 10 centimeters, so the error will become 2 centimeter. So this error will keep on changing with time, since this all the modeling that we are doing is for unsteady state. Basically, we want to capture the time dynamics also. So what proportional controller will do is it will take the control action on the basis of the magnitude of this error. So if the error is high, the control action taken would be higher. If the error is low, the control action taken would be lesser. So basically the control action is proportional to the error. That is proportional to the error. So on the basis of that, we can write the controller output as this term. That is, the control action is equal to the sum of some constant value, that is bias value, plus Kc, that is the controller gain, and then the error term. So the final equation of the controller output will become Pt is equal to P bar plus Kc into E times T. So this is the steady state value that is usually provided. Now, few of the key features of the proportional controller are that the controller gain, that is the value of Kc, can be adjusted to make sure that the controller output changes are sensitive as desired to the deviation between the set point and the control variables. So basically, let's say if my level changes by 1 centimeter and I want to open the valve by 100%, so that I can do by keeping the value of Kc to a high value 100. Let's say for a level change of 1 centimeter, I only want to open the valve by 2%. So corresponding to that, Kc will become, let's say, 2. So we can control the sensitivity of the output. We can control the sensitivity of the controller output by changing the value of the Kc. That is what this first point means to say. Similarly, the second point says that the sign of Kc can be chosen to make the controller output increase or decrease as the error signal increases. That is, if level increases, then we want to open the control valve. So in that case, if you want to do that if level increases, open the control valve. In such a case, you can write the value of K as positive. Let's consider it as positive. And if in the opposite case, that's the level decreases, and in case of level decreasing, then we want to open the control valve. In such a case, we can just change the value of the controller gain to the opposite of the whatever was the earlier term. So if this is negative, this will be positive, and if this is positive, this will be negative. So this will be its opposite action. So that is, we can change the sign of the Kc such that the controller output will increase or decrease on the basis of the error signal. Now in physical controllers, in many of the physical controls, we don't have this Kc term to be tuned, but we have the inverse of that. So, and that the inverse of that is known as proportional band. So that is basically defined as 100% upon Kc. So basically what it signifies is that a small proportional band, that is for a less value of proportional band, it corresponds to large controller gain, whereas a large proportional band implies the small value of Kc. So you will see this proportional band terminology in many scenarios. Then here we are having the graphs related to the controller output and the controller input, that is the error. So that is, if error increases, this is for proportional controller. That is, if error increases, then according to the control law, this proportion, the control action, that is P, will keep on increasing. But say in physical system, we can't just keep on increasing the controller output to infinity. So we need to limit its value. So we provide an upper limit or the lower limit to the control action generated, that is given by P max and P minimum. So this is the actual behavior of the proportional control that is being observed in the physical systems. Similarly, if we want to write the transfer function of these equations, that is, we are having this equation. In order to obtain the transfer function in terms of output upon input, we can just find the Laplace transform of this equation and we can get the transfer function given by this equation. That is, Kc is P by E, that is the control action upon error. So then one disadvantage of the proportional only controller is that the steady state error or offset occurs after a set point change or sustained disturbance. That is, let's just consider. So over here I am changing my input. That is, I'm changing my set point. So ultimately, if this was a perfect system, ideally the set point should be reached if we are using an ideal controller. But in case of proportional controller, this set point won't ever be reached. So what we will physically observe is we will be seeing a constant offset. So after the steady state has been reached, there will be a constant offset in this proportional controller. So this can't be minimized using this proportional controller. But in order to mitigate this offset or reduce this offset, we can then use the integral action. So that is the integral controller or the integral action we will be studying next. So in proportional controller, the output was proportional to the error. So we didn't have any information about the past control actions or the past of this error. So what was the history of the error, whether it was increasing, decreasing. We don't utilize any of the information of this. Whereas in case of integral control, the control output depends on the integral of the error signal over the time. So basically it will also consider the past errors and it will calculate the integral of that error, and on the basis of that it will take the control action. So yes, this is the equation corresponding to a integral controller. That is, the output will be again some constant bias plus 1 upon tau I. So this is the parameter specific to the integral controller. Then 0 to t, error, and dt. So this ti is an adjustable parameter referred to as integral time or the reset time and has units of time. So this has also been referred to as reset or floating control. So yes, integral control action is often widely used because it provides an practical advantage, that is elimination of the offset. Although elimination of offset is usually an important control objective, the integral controller in equation 8.7, that is this equation, is seldom used by itself. So we can't use this integral controller alone. We need to use it with proportional controller, because in case of such a controller, this control action will be only taken after this much amount of time has passed. That is, it says that until the error signal has persisted for some time. In contrast, the proportional control action takes the immediate corrective action. That is, if I want to just draw a rough diagram. So if over here I'm changing my set point, so the proportional, as soon as this set point is being changed, proportional control action will start taking the action. Whereas in case of integral controller, it will start taking the action after after some amount of time has passed, that is, error has sufficiently accumulated, then only it will try to take the control action. So what we do is, in most of the scenario, we use the combination of integral control action with any other controller. So that is, we use the proportional controller with an integral controller and the corresponding output to that PI controller. So this is also known as PI controller, and it is shown by this equation. That is, P bar plus Kc is the controller gain from the proportional controller. Then this term we obtained from the integral control action. Now we can take the Laplace of these equations and we can find the transfer function corresponding to this PI controller. Now if we want to study the response of the PI controller, we can see it from this graph. So basically this is the error signal, that is our change in the input. So at time equal to 0, I am introducing a step change in the error. That is the error, and corresponding to that we can see the output. So as soon as the error is changed, due to the presence of the proportional controller, the response will shift by the magnitude of Kc depending on the controller gain, and then the response will keep on rising depending on the slope of this basically slope of this Kc upon tau y, and then it will keep on increasing. So if you want to just find the equation of this plot, we can take the inverse Laplace of this equation and provide the step input of, let's say, 1 by s. Provide the step input of 1 by s and then take inverse Laplace, and then we can find the equation of the equation in terms of time for this step input, and on plotting that we can get this graph. So one disadvantage of the integral control action is that it produces the oscillatory response of the control variable, and it reduces the stability of the feedback control system. So if we use the integral control action, then the order of the system will increase by 1. So if we are using an integral controller action in a first order system, so it will become a second order system. And in many cases, and in most of the cases, it will produce the oscillatory response due to the presence of these integral systems. However, a limited amount of oscillations can usually be tolerated because it is often associated with a faster response. So yes, if I want to reach this set point due to the presence of integral control action, it will keep on oscillating and ultimately reach the set point very fast. So even though the oscillations are there, it will help us to reach the set point faster as compared to the proportional controller. In the case of proportional control, it will never reach the set point. And also the undesirable effects of too much integral control action can be avoided by proper tuning of the controller or by including the derivative control action, which tends to counteract the destabilizing effect. So now we will study about the derivative control action, but before that there are some features. That is, for integral control action, the offset will be 0. So it is slower, but has an oscillatory response, and it can result in an integral wind-up, typically used in flow control or temperature control. Now we will study about the derivative control. So the function of the derivative control is to anticipate the future behavior of the error signal, considering its rate of change. So again, to repeat, proportional control takes the corrective action as soon as the error is reached, whereas the integral control action will take an error after the sufficient amount of time has passed. That is, it will take the integral control action on the basis of the past error. Whereas what this derivative control action is, it will anticipate the future behavior. That is, this is present, this can be called as past, and this anticipates the future behavior of the error signal depending on this derivative. So let's say if my error is increasing in the positive direction, so what this controller will do is, it will just calculate the rate of change of this error. On the basis of the rate of change of the error, that is d by dt, it will take the control action. So the model for this derivative control is given by this pt equal to p bar plus tau d plus this d by dt of error. Then in order to find the transfer function of this, we can take the Laplace transform of this equation and we can get this equation. So that is basically, by providing anticipated control action, the derivative mode tends to destabilize the controlled process. Thus it is often used to counteract the destabilizing tendency of the integral mode. So we studied that the integral control action can have oscillations and it can lead to an unstable system. So in order to stabilize that, what we do is we anticipate the future errors, and then accordingly we take the control action such that the integral action doesn't destabilize the system. Then we are having this. So over here you can see that this important point, that is, if the measurement is noisy, that is, it contains the high frequency. That is, let's say if the measurements is noisy, that is, it keeps on fluctuating across a constant point ym. So over here you can see the rate of change of error is very high. However, if we take a look on the longer term, the error is almost constant, but it is just fluctuating. So that is, when the measurements are noisy, that is, it contains the high frequency random fluctuation, then the derivative of measured variable will change widely and the derivative control action will amplify the noise unless the measurement is filtered. So basically this error will keep on happening, and since the error is happening, the derivative control action will keep on amplifying, so it will take the control action very frequently. So what we need to do is we need to take the filter. So when we say filter, we can just sum few of this segment, so it will become a constant value, then sum this segment, so it will again become some constant value. So we can use a filter to eliminate or reduce the amount of noise present. Consequently, a derivative action is seldom used for flow control because the flow control loops respond quickly and flow measurements tend to be noisy. So we studied that if integral control actions are used when we are having flow control, temperature control, but as mentioned that flow control can be noisy, and since it can keep on changing very frequently, that is why we can't use this derivative action or for this flow measurements. Now the other last controller that we are studying is the proportional integral derivative controller. So what we do in this thing is we add the integral action as well as derivative action, and then we are having this constant controller gain from the proportional controller. So we combine the effect of each of these three controller by using the parallel form. That is basically we are summing each of those three control actions in order to reach this control output. And then we can again find the Laplace transform of this equation in order to find the corresponding transfer function of the PID controller. So this equation you need to remember that this proportional control action will be controller output upon error will be Kc controller gain times 1 upon 1 plus tau is plus tau ds. So this is the integral time and this is the derivative time constant obtained from the derivative control. So this is the parallel form of the PID control. There can be multiple forms of the PID controller also. So they are shown. So there can be, so these are also form of PID controllers. So depending on how we define the control output equation, so we can have multiple forms of this PID controller. So what we are right now studying is the parallel form, that is this form. Then we can add a filter to overcome this derivative action, so that is provided over here. Similarly, there are this other form, so we only need to study about this kind of parallel form of the PID controller. So this is the slide from the lecture. So over here we are just comparing each of these three controller. So the first one is P control, that is simple to implement and fast, but it cannot guarantee a offset free response. So the response will have offset in most of the cases, whereas this PI control will give us the offset free response, but it slows the process dynamics and introduces the oscillations. Now the ultimate one is the PID controller. It gives offset free response and has a relatively faster response. However, it is difficult to implement optimally. That is, we need to find the optimum parameters, that is Kc, tau I and tau D. These three parameters will decide the performance of the PID controller. So these three parameters we need to find optimally. What we usually do is we start with P controller. If the offset is not desirable, then we go for PI controller. And if the response is sluggish, that the controller takes a large amount of time to respond, then we can go for the PID controller. And ultimately the response, the selection of optimal values of Kc, tau I, tau D is known as controller tuning. So I think we will be studying different kind of controller tuning approaches, whereby we will be studying how can we obtain these parameters. So one such approach is known as direct synthesis, that we will be studying, I think, in next couple of lectures, after 2 or 3 lectures. So over here we are seeing the closed loop responses of the PID controller, of the combination of this PI, PID controller for FOPTD model. So basically FOPTD is this simple first order process, that is Kp upon tau s plus 1, and then we have this time delay term e raised to minus of tau d upon s, let's say minus TED upon s. So this is our FOPTD model, and if I provide the step input of, let's say, 1 by s to this system, So what all kind of characteristic curves of the PID controller or the PI controller observed is being shown in this graph. So this is corresponding to the simple open loop process. So this is the response of a first order system, and since we are having the delay term, we can see the delay present over here. So this will be tau d. Now then we can take a look on this PI controller. So let's say if we had to look on the response of the P controller, so it will simply, so over here you can see ultimately it will reach the set point, but the P controller would never be able to reach the set point. Whereas no, the set point is over here. So our main target is to reach this zero set point. So P controller would never be able to reach this what set point. So that is being observed from this plot. So this is our P controller. So as soon as the step change of the magnitude 1 is being introduced, we can see that the P controller will take the control action, but it won't reach the set point. Whereas in case of this integral control action, we can see that the controller will take the control action, but it will take some time eventually to reach the set point. Whereas in case of this PID controller, we can see that it will reach the desired set point faster as compared to the PI controller. So this is for PID controller, this is for PI controller, and this is for proportional controller. Similarly, these are the plots for PID controllers. That is, if we keep on changing the values of Kc, then what kind of controller action we can see. So the main objective of studying is this graph is, if we just keep on changing the values of Kc, that is, if the Kc was the optimal one, then we can see the control action can be reached very smoothly. Now if we decrease the value of Kc by 50%, then we can see the time taken to reach the set point will decrease. However, if we increase the value of Kc by 50%, then you can also observe this oscillatory behavior, and it may not reach the set point quickly. So this Kc can introduce this oscillatory behavior, it can introduce the delay of the process. That is the main objective to study this graph. Then similar effects are observed in this integral time also. So if we keep on increasing the integral time, so the delay in order to reach the set point will increase, so longer time will be taken to reach the set point. And if we decrease the integral time, then the response will become faster, but however, if we are taking a look on combination, it may become oscillatory for most of the cases. Then similarly, these are the results for the tau d, that is the derivative time from the derivative control action. So the response can become oscillatory for different values of tau d. So basically, each of these parameters can have effect on the controller output, on the controller output. That is, we need to carefully tune these process parameters Kc, tau I, tau d. So that will be our main objective after we studied about the stability of the system. So given this controller parameter, we will see whether the system is stable or not. If the system is stable, then we are good to go. We can use these controller parameters. However, if the system is unstable, we need to carefully choose these values of Kc, tau d in order to make the system stable. So now we will just study in brief about reverse or direct action. That is, the controller gain value of Kc can be either positive or negative. For proportional controller, when Kc is greater than 0 and the controller output increases as, that is, let's just write it over here, Kc is greater than 0, controller output increases as Y measurement decreases. So such a kind of action is known as reverse acting. Similarly, for this system, if Kc is less than 0, then it becomes direct acting. So these are just terminologies that we need to remember in order to find the kind of control action that we are using. So that is, so over here we can see that when kc is less than 0, the controller is said to be direct acting because P, that is controller output, increases as measurement increase. That is, if you have to consider the example of level control, if the height of the level tank increases, then we have to open the control valve. That is, the controller output should also increase. So such kind of system is known as direct acting. That is, with the increase in level, you need to increase the control valve opening. That is direct acting. Now let's consider a case of this first order reaction occurring in the CSTR, and we are monitoring the temperature of the reactor, and let's just we are providing steam to the jacket. So if the temperature of the system increases, we need to control the temperature of the reactor. That is, we need to decrease the steam input to the system. So what we will do is we will close the control valve. So such kind of system will become reverse acting, and in such a case the Kc value will be less than 0. So that is what we mean by when we say reverse action or direct control action. So over here we are having plot of that control actions. So the first one is reverse acting, that is Kc is greater than 0. So over here we can see that if the error increases, that is, if the measurement will increase and the corresponding error will increase, then the controller output will also increase. Whereas in case of direct acting, if the error increases, the controller output decreases. So on the basis of that, we can just find whether it is direct acting or reverse acting. Then the last kind of controller is this on-off controller. So in all the earlier cases, we saw that the control action will depend on one or other form of error. That is, basically it will depend on the magnitude. It will depend on the magnitude of error. Whereas in case of error controller, it won't depend on the amount of error. It will just depend on whether it is happening in positive direction or whether it is happening in the negative direction. So basically, on-off controllers are simple, inexpensive feedback controllers that are commonly used as thermostats in home heating systems or refrigerators. That is, whether we want to, for example, in refrigerator, we don't control the temperature, we just increase the refrigeration. We just use this on-off controller in case of this refrigerator. They are also used in non-critical applications such as some level control loops and heating system. However, on-off controls are less widely used than PID controls because they are not versatile or effective. So let's consider level control example over here. So in such a case, what is it? Rishabh, you can see the recorded section. If you just go on the NPTEL website, over here you are having this problem solving session August. So if you just click on that link, it will take you to this click here. So over here you can see the doubt clearing sessions of each of these sessions. So these sessions are being conducted by me, and these sessions are being conducted by my colleague Rashid. So over here, if you just click on the YouTube link, you can see. So this was the content discussed in the last lecture. So in last lecture, we were studying the second order system, so that can be obtained from here. Similarly, you can find the slides that we are discussing in this folder. So over here, week by week, I have just given the slides as well as the related notes. So these are just the slides that we are discussing. So this will be usually available after the day of conducting this session. So you can watch these videos also. So yes, as discussed, For an ideal on-off controller, the controller output only has two possible values, whether it is opening or whether it is closing. So yes, the disadvantages of the on-off controllers are that it results in continual cycling of the controlled variable and produces an excessive wear on the control valve. The later disadvantage is significant if control valve is used, but less of a factor if solenoid valves or solenoid switches are used. So basically, what happens in control, on-off control, is the valve will keep on opening and closing very frequently. So that may lead to wear and tear of the control valve. However, this won't be of more important if we are using the solenoid valve or solenoid switch, but if we are using a control valve, then this will become more important. So it's just to give an overview, we had studied this kind of controllers: P controller, PI controller, and PID controller. So in next class we will be studying about this all topics. So today we will be starting with these lectures, starting with solving the numericals. So this is our question number 1. So right now it is around 8:02 p.m. So I will give you around, let's say, 8 minutes to solve this question, and we can discuss the solution at 8:10 p.m. So the question is, an electronic PI temperature controller has an output of 12 milliampere when the set point equals the nominal process temperature. The controller responds to a step change in the temperature set point of 2.5 milliampere equivalent to a change of 5 degrees Fahrenheit is shown below. So using this table, we have to find the value of Kc and tau I, and we have to comment whether the controller is reverse acting or direct acting. That we have to comment. So yes, you can try solving this. I will discuss the solution after a couple of minutes. जीमेल जीमेल पर लॉगिन करने सेम पासवर्ड છે જોઈ લે પાસવર્ડ ના તમને મેસેજ કરો હું કરું બરાબર જીમેલ નો પાસવર્ડ હું મોસ્ટલી સેમ જ સમય જોઈ લે તે મેસેજ હું કરું બરાબર Just give me a minute. So let's start with solving this question. Sorry for the delay. So the question states that we are given a PI control and corresponding to that we have been provided this data, and on using this data we have to find the controller parameters, that is Kc and tau I. So let's solve this question. So we have been given a PI controller. So for PI controller, we know that the transfer function is P upon S upon E by S is equal to Kc into 1 plus 1 upon tau I S. This is what we are given. We already know. And in the question, we have been given, let's just plot this. So over here, we will be having time. And then we are having control action P. Over here we are having 0. So it is given 0 minus, it is 8. So let's just draw it over here. So in this direction the value is 8. So this is 8. So this will become 4. This will become 6. Then we have been given at 0, it becomes 6.7. So this will be 7. So over here it will become 6.7. So then after at 20, so we are having 20, 40, 60, 80. So at 20 it becomes 6. then at 60 it becomes 4.7. This number over here. So this is 6.7 and this is around, this is 6, then it will become 4.7 and ultimately at 80 it becomes 4. So we can see such a kind of slope, and after 80 we have nothing, so let's just consider it as constant. So we have been given this much amount of information. Okay, I think this is a incorrect plot. Let's just draw it on a bigger scale. Eight, 4, 6. So at time t equal to 0 it is simply 8, and at time t equal to 0 it becomes this 6.7 over here. Then we are having 20, 40, 60, 80, and at 80 we are having the value of 4. At 60 we are having the value of 4.7, and at 20 we are having the value of 6. So we can just draw a kind of plot through this. So basically the response is given by this curve of the PI controller, and using this data as well as the information that we are having, we have to find Kc and tau I. So over here we are given the plot between P of time and versus time. So what we can do is we can just find this equation in terms of time given the step input. So here we have been given a step input of 2.5 milliampere. So the error signal we can write it as 2.5 by S, so that we can feed it over here. So P of S will become 2.5 times S into Kc into 1 plus 1 upon tau I S. So let's just write it as M, step change of magnitude M, so that we can get the generalized form of the solution. So now we can just simplify this and write it as M times of K into C upon S plus M times Kc upon tau I into S square. So this is our P of S. Now since we want to find P of t, we will take the Laplace inverse of this equation, and it will become Laplace inverse of M Kc by C plus Laplace inverse of M Kc on tau I into S square. So Laplace inverse of 1 by S is simply 1. So this will become M Kc, and 1 upon S square is simply t time. So it will become M Kc upon tau I into time. So I hope this derivation is clear. So you can also straight away remember this formula. Meanwhile, if you have any doubt, you can ask. So over here we can see that this is a equation of the form of y equal to mx plus c. So this is our output. So this is our intercept c, plus this is the slope, and this is our x. So this intercept that we are having over here is equal to mkc, and the slope we are having is mkc upon tau I. So we can see the intercept is basically this term. So this term over here is mkc, and the slope will be mkc upon tau I. Since the earlier steady state value, that is earlier the value of the proportional controller was 8, we considered this as our MKC. So basically MKC is 8 minus 6.7. So this we obtained from the chart. This is 8 minus 6.7. So it will become 1.3. The value of M, that is the step input, was 2.5. So Kc will become 1.3 upon 2.5. So this will come around 0.52. So this is our value of Kc. Similarly, we can find the slope of this curve. It is the slope of this graph using the data also. So you can use any two data sets. Over here for 20 seconds, the change is around 0.7. So over here also for 20 seconds, the change is around 0.7. For over here for 40 seconds, it is around 1.3. That is approximately equal to 0.65. So correspondingly, you can take any value, or you can also find the average value. So let's just consider the slope to be 0.7 plus 0.7 plus, it was 0.65 into 2 upon 1, 2, 3, 4, 4. So this is basically nothing but we are calculating the weighted average. So it will become 1.4 plus 1.3 by 4, that is 2.7 by 4. I think this is the same thing you would be getting from here. So that is over here. The slope is basically 2.7 divided by 4, and then on the bottom also, so we have to also divide it by the y-axis, that is 20. So the step change was 20. So slope will become 2.7 upon 80. Let's just calculate it. So it becomes 0.3375. So and the slope we calculated analytically as MKC upon tau I. Now MKC we already found out as 8 minus 0.67, that is 1.3. Or you can also use the value of M was 2.5, Kc we calculated as 0.52, so ultimately it is 1.3 upon tau I is equal to 0.3375. So that will become, I hope I am audible. Okay. So basically tau I will become 1.3 upon 0.3375. So I think over here we are having a 0 also, 0.03375. So ultimately the value of this we calculated, tau we calculated as 38.5 seconds. So the value of Kc we got it as 0.52, and the value of tau I we got it as 38.5 seconds. So this is how we calculated the controller parameters given the data that we were having. Now we have also been asked whether the controller is reverse acting or direct acting. So we studied about reverse acting and direct acting in earlier slides. That is, we studied one plot. Okay. So over here, the first one was this. This is reverse acting, and this one is direct acting. So in our case, we had observed that with increase in the error, the output was decreasing. That is basically this plot. With increase in error or with increase in time, the error, the response is increasing. The response is decreasing basically. And also the value of Kc, over here is less than 0. So that is basically, we can see as soon as we introduced a step change, that is error increases, the value of the output decreases. That is, the control action is taking in the negative direction. So with increase in the error, the action is being taken in the opposite direction. That is, for such a case, the value of Kc will be less than 0. And for such a case, we can say that the controller is a direct acting, because the value of Kc is less than 0. Also, since with the increase in the step change error, the output was decreasing. Over here, we are having an alternate representation of the graph, that is, with increase in the error, the output is decreasing. Whereas in case of our plot, we were having a step change and then the output was decreasing. That is why we said that the value of Kc is less than 0. That is why we call it as direct acting. However, if the graph was increasing, that is, at this point it increased and that keep on increasing, then we would have said it was a reverse acting. So I hope that clears the solution. So this is the question number 2 that we are solving, which is very similar to the previous one. So over here we have been given the plot and have been asked if the measured input to a PI controller is a step change, that is, input Ym is a step change of 2 by s, and the controller output changes initially as shown in the figure 8.6. So this is our controller output, and we have been asked what are the values of controller gain and integral time. So given this plot, we have been asked to find Kc and tau I. So this question is very similar to the previous question. So I will just give you around, let's say, 3 to 4 minutes. So right now it is 20:28. We can discuss the solution by 20:30. That is 2 minutes. You can try solving this on your own. So let's solve this question. Again, this is very similar to the previous question. In the earlier question, we were given the graph. We were given the data, we had constructed the graph and then calculated the generalized equation, and on the basis of that, we calculated the slope in the basically the gain. Now over here, we can see that we have been given an input of 2 by s. So since the system was earlier at constant value and this the measurement is being changed by the step input, the error will also be the step input, so this will be ultimately the form of the step input also. Corresponding to that, we already found this generalized equation in the earlier this equation, that is Pt is equal to m times of Kc plus mkc upon tau I into t. So this term is usually p at given time minus p at steady state. So that is why we usually observe the intercept. Now over here the steady state is, this term is 0. So if we put the value of t equal to 0 in this equation, then we can see that this value will simply become mkc. That is basically this term is mkc. Whereas in the case of earlier, this value was not 0. It was, I think, 8. That is in the earlier question. This constant value is 8. That is why we took the difference of both of this term when we put the value of 0. So yes, coming back to this question, the value of mkc is 0. Similarly, the value of the slope mkc upon tau I is 1.2. Now we can use this information to find the value of the controller, both of these things. The value of m, that is the step change, is here is 2. That is, we can get the value of kc as 6 by 2 is equal to 3, whereas the value of tau I will become mkc upon 1.2. The value of mkc is 6, so it is 6 upon 1.2, it is 5. That is the value of controller gain. Kc is equal to 3, and the value of integral time tau I is 5. So that is how we solved the question. So now we will be taking a look on this next question. So this is the last numerical that we will be discussing today. After that, in the next class, we will be discussing the questions related to the block diagram representations. So let's just solve this question number 3 right now. So the question states that an electronic PID temperature controller is at steady state with input of 12 milliampere. The set point equals nominal process temperature initially at T equal to 0. The error signal is increased at the rate of 0.5 milliampere per minute equal to the rate of 2 degree Fahrenheit per minute. If the current settings are Kc equal to Kc equal to 2, tau I equal to 1.5 minute, tau D equal to 0.5 minute, then we have to derive an expression for the controller output Pt. Repeat the first step for tau D equal to 0 and plot the two controller output and qualitatively discuss their differences. So for the given parameters, we have to derive an controller output for Pt and then repeat the same for tau equal to 0, that is a PI controller, and then discuss the compare basically PI controller and PID controller. These two controllers we have to discuss. So you can try solving this question. So right now it is around 20:37. We can discuss these questions after 8 minutes, that is around 20:45. So once we are done with the solution, we can wrap up today's class. Meanwhile, if you have any doubt, you can just write it in chat box or ask, and we can discuss it. So I think you should be able to solve this. This is again similar to the previous questions, but in this case, rather than the step input, we have been given this constantly increasing input with the rate of 0.5 milliampere per minute. So basically, you can see that this input increases with a constant slope of 0.5 per minute. So over here, this is time and this is input. So basically, we are having a ramp input of that can be represented by this equation 0.5 t. So keeping this in mind, that this is a ramp input, we can solve it using the approach that we discussed in the earlier two questions. So let's just solve this. So the error signal is given by 0.5 t. So in terms of S domain, we can take the Laplace transform of this equation and we can write it as the Laplace transform of t is, I think, 1 upon s square. So it will become 0.5 upon s square. Then the steady state value is 12 milliampere. That is not of use to us right now. Then at t equal to, let's just plot this curve. Milliampere per minute. This is error and this is time. And then we have been given the PID controller parameters and we have to find the expression of controller output in terms of PT. So for PID controller, we have this transfer function model as P by S upon E by S. PS upon ES is equal to KC 1 plus tau ds plus 1 upon tau is, and we have been given these parameters, and es also we calculated it as 0.5 s square. That is, we can write this as 0.5 s square kc 1 plus tau ds plus 1 upon tau is. So this is the equation using which we can calculate the PT by taking the Laplace inverse. So let's just simplify it further. So it will become 0.5 kc upon s square plus 0.5 tau d kc upon s, and s will become s plus 0.5 kc upon tau is cube. We can replace the values also, so it is 2, 1.5 and 0.5. It is 0.5 into 2 upon s square plus 0.5 into tau d is 0.5. Kc is 2 upon s plus 0.5 into kc is again 2 upon s cube. Value of tau I is, I think, 0.5. Value of tau I is 1.5. So simplifying this further, we will be getting 1 upon s square plus 0.5 upon s plus 1 by 1.5 s cube. Now we can take the Laplace inverse of this to find P of t. So Laplace inverse of 1 upon s square is, we studied it as 2. So this 1 upon s will be 1, so it will simply 0.5 plus s cube will be t square by 3, t square by t square by 2, so it will become 2 into 1.5 is 3, so basically it will become t square upon 3. Now this is basically a deviation variable, and the steady state value was 12 milliampere. So basically P of t minus 12 we found out as 0.5 plus t square by 3, that is P of t is nothing but 12.5 plus t plus t cube by 3. So this is the equation of P of t that we found out. Now what we have to find? We have to repeat the same if tau d equal to 0. So the term corresponding to tau d is this middle term. So if tau d equal to 0, this entire term will become 0. So this 0.5 won't be there. That is for PI controller. P of t will become, this will be missing, so it will become 12 plus t cube by 3. So this is for PID controller. This is for PI controller. So I hope this much is clear. Okay, there are no doubts. So now what we have been asked is we have to plot the controller outputs and qualitatively discuss their difference. So basically we have to plot this P of t with respect to time and then discuss their differences. So let's just plot the curve over here. Time and P of t. So let's just consider this as time 0, 1, 2, 3, 4, 5, 6. So at time t equal to 0, the value of steady state we were given as 12. So this is 12. And for P, let's just draw first this PI controller. For PI controller, time t equal to 0, the value is 12 plus 0 is 12, and then it increases if the value, if we put time t equal to 1, so it will be 13.3, and then it will be increasing according to this third order term t cube. That is, it will keep on it will be having such a graph. Now if we take a look on this, so this is corresponding to PI controller. Now for PID, we are having 12.5 plus t cube. So that is at t equal to 0, the value becomes 12.5. And then the trend will be similar to the previous curve PI controller. That is, it will be like this. So this red curve is corresponding to PID controller, whereas this blue curve is corresponding to PI controller. So from the graph you can see that both of this curve have similar shaped responses. So the response is similar, but the only difference is at time t equal to 0, there is this sudden jump in this PID controller, and that is due to the presence of the derivative term, that is tau d, or else the behavior of both the curves would have been similar. That is, we can also say that the derivative term in the controller gives a jump start when the set point begins to change, that the PID controller doesn't have. So due to the presence of derivative controller, due to the presence of derivative term, we have this jump start over here. So I hope the solution to this question is clear. Now in the next question, we'll be solving few of these questions related to the block diagram representations. So these questions are basically related to the stability analysis that we will study using the direct substitution method, roots array, this Bode plot, that all things we'll be studying in the next class and solve the questions related to that. So meanwhile, if you have any doubt related to any of the questions or theory discussed in today's lecture or any of the assignments, you can ask in chat box. I will be available for around 5 minutes. After that, we can end today's session. So since there are no doubt, we can end today's lecture and hope to see you in the next class. Thank you for joining.